Phone. Well, good afternoon. I'm sitting in California. I'm in Orange County, California, in a city called Yorba Linda right now in our one of our locations that is an office laboratory. And so it's not evening yet, and I know our deck is going to say good evening, but I'm going to say good afternoon because it's 3 o'clock here. So welcome everybody. My name is Bob Schweitzer. I'm the CEO of Astera Technologies Corporation. And today we're going to give a brief presentation about the background of our company and the technology that we're focused on. And we may show you a few other things, and then we'll open it up for any questions you might have. So Astera Technologies was created a little over a year ago. It's focused mainly on graphene and the production of graphene. So we had originally been involved in a process of converting plastics to graphene, and as we did that, we got deeper into graphene as an advanced material. We became an advanced material company, and so we're focused on graphene. And this presentation is going to be about monolayer or crystalline form of graphene and our breakthrough technology as it pertains to monolayer graphene. So I'm just going to start off here with the presentation. Hopefully everybody can see it. And if somebody's having some trouble, just raise a hand and we'll try to fix the problem. But okay, so artificial intelligence. AI has a physics problem. Mainly we have power, heat, and actually the hidden race to build the next layer of computing, and that's what we're involved in. So we're about the layer or the substrate underneath what is actually a logic device and or a memory device. So next page. Okay, so that's me. They always want to say something about who's speaking, and that's me. So that's me. I'm Bob Schweitzer. I'm 62 years of age. I got 35 plus years under my belt in various business ventures and a great deal of work with respect to startups in particular. And so helped companies grow. I've done a lot of work inside of restructuring companies as well. So Astera Technologies is really inside of a startup mode inside of a year. So my effort here for the company as the CEO is to help launch this company, and proud to be sitting in this position. Okay, so the story behind the artificial intelligence headlines. Everyone sees the apps and they see, ChatGPT, and they see a lot of that and they're interacting with it. And but few people see or understand the infrastructure and the constraints behind it. You can see on the left there the amount of global electricity consumption by the year 2030 that the data centers are expected to be demanding. And there's going to be some 300,000 times growth in computing in AI. This dates back to 2012, but takes it forward. So you can see that the energy demand and the growth for it and the demand are enormous. But there's sort of devices are lagging. And so, at the same time that they're having difficulty manufacturing to meet demand for chips, there's the issue of speeding everything up without some of the issues that we know exist in the current structure. So today, I want to talk about the physical world and how that keeps up with artificial intelligence demand. So AI is really connected to utilities, in fact, but it's moving into the utility markets and having to make adjustments, frankly. I mean, the policy out of DC right now is go ahead and build your data center, but bring your own power. And there are other things that are happening. So, the local communities where you see the installations in the rural areas, you see, these town hall meetings awfully disrupted with unhappy folks. And so it's really affecting the grid. And the AI story has crossed over from software into power, grid capacity, and industrial infrastructure. So some of the headlines, um, show that you've got power companies. They're really consolidating around data center demand. They're having to make adjustments on their own, and AI data centers are changing electricity demand forecasts. The power availability is becoming a gating factor for where compute can be built. And as a result, the bottleneck is shifting from pure chip supply to the entire physical stack. So we've got a quote there that the new AI arms race is not just who has the best model, it's who can power, cool, and connect the infrastructure underneath it. And that's where we come in. So the bottleneck moving deeper into the stack. So the visible layer that we all see is the software. The limits are really underneath and it's the hardware. So the deeper the layer, the harder it is to change, and the more defensible it can become if solved. So the public debate focuses on models and GPUs, but really the next constraints may sit in the interconnects, heat transfer, manufacturing, and materials. And so that's where Astera believes the next layer of computing is forming, and that's where we lie. Some of the things here on the right talk to some generalities, but it also mentions networking in photonics. And photonics is where we sit. So we're involved in, and you're going to see this in the next slides coming up, we're involved in a substrate that works with photonic compute and memory chips. And it's meant to replace silicon. And a lot of what the bottleneck's about is that the silicon solution is basically obsolete. And when you're going to move into photonics and away from electronic semiconducting, that photonic device needs to sit on something other than silicon because it's only going to impair the photonic efficiency. So we're focused as an advanced material company on a substrate with graphene for photonics. So next slide. So heat's not, it's not a side effect. It's actually a design constraint. Faster systems mean little if the infrastructure cannot manage thermal load. So, and when compute density rises, three things happen at the same time. More energy is pulled into the data center, more heat must be removed from the chips and racks, and more data must move with less latency and lower loss. And what's uncomfortable about the truth here is that the future of AI may depend as much on the materials engineering as on the algorithms. And we recognize that. So the migration from electrons to photons. So why is the industry looking to literally light, for faster, lower loss data movement? Well, electronic systems move information through electrons and copper pathways. Photonic systems use light to move information with potentially higher bandwidth and lower thermal burden. For artificial intelligence factories, faster data movement between chips, racks, and clusters is becoming essential. So if you want to put a practical statement on it, think of it like replacing crowded city streets with high-speed optical highways. So as a facilitator of this shift in technology, the materials layer that nobody's really talking about is what we address. And a photonic future still needs manufacturable, scalable substrates underneath it. Photonic systems need materials that can support speed, heat management, and optical behavior. Many materials show promise in research, but really fail in commercial production. And the winning layer may be one that works with existing manufacturing workflows. Since, excuse me, science gets attention, manufacturing creates adoption. And so we are a manufacturer of material. On the subject of graphene, why is it interesting? It's not new, but why is it interesting right now? Well, it's not because it just sounds exotic, because that's a neat name, but its properties map directly to the bottleneck that we're talking about. It's relevant where heat limits intensity on the thermal pathway. It's optical behavior. It has a potential nonlinear optical application. It's thin. It's a thin material layer. So the potential fit with wafer scale substrate strategies works, and it's tunable. We can adapt it to photonic chips and systems. So our thesis at Astera is graphene can become more than a research material when it becomes produced consistently and integrated into the commercial photonics stack. And that's what we've resolved. Commercialization is the challenge. The question's really not can it work once, it's can it work readily, reliably and at scale. So here you have a 1 through 5 sort of a schematic, of getting past your research and into production, and that's where we are. We're into production. We've gone through the research, repeatable process. We are moving into production as we speak, and beyond the presentation, we can get into some discussion about how we're actually making our substrate to the extent that the deck doesn't address it. We can get into some more details. So most advanced materials die between the lab and the factory. That's a fact. Astera is focused on the bridge: defect control, process repeatability, wafer scale thinking, and integration with real manufacturing workflows. And what needs to be true for this all to matter? There needs to be a practical framework for evaluating any next generation materials platform. That's a fair question to ask us. So do what we do, does it solve a real bottleneck in the power, heat, data movement, or manufacturability? Answer is yes. Can it be made repeatedly, not just in the lab, through controlled production? The answer is yes. Can it fit existing workflows? The foundry compatibility matters for adoption. So existing foundries, can we match up with them? The answer is yes. Can it unlock multiple markets? Well, there's no question. If you all have studied photonics, we've been moving data on light for some time now. The issue is computing in light and what's that sitting on. So photonics and AI infrastructure and adjacent compute system, those are the multiple markets we're addressing. The bottlenecks, it's real, and the materials layer matters, and we recognize that, and we're addressing it, and we're commercializing it. So our pathway here to solving the bottleneck and what we're doing is it's built around production integration and downstream relevance. We produce the material, we produce wafers, we're integrating with foundries and photonic computing systems. We have strategic alliances in this space, including data center. And so we're not involved in a better app. We're building the structure to make the app run, and we scale it, and we can. So the bottleneck's no longer just computer power, it's the infrastructure underneath it. Again, power, heat, bandwidth, materials, and manufacturing. Our answer is graphene infrastructure for photonic chips. We're just strictly focused on the materials layer and how that materials layer actually facilitates the efficacy and the most efficient ability of the photonic device. So the bottleneck's not just the computer power, it's the infrastructure underneath it. We're already building it, and we're excited about that. So we're going to get in. This says any questions. We can get in any questions. I wanted to, do we have Larry on the line?
I'm here.
Hey, Larry. So Larry Daniel, who's one of our technology officers here at Astera, he's on the line here, and we want to talk a little bit more deeply about how we make the graphene substrate, monolayer graphene substrate for a photonic application. Um, we use a chemical vapor deposition process, and our particular manufacturing capabilities are perhaps the most unique in the world. And Larry, can you go ahead and give a little bit of background on the CVD process that we use?
Absolutely. The CVD process that we have used in connection with our substrate has required our partners who make the machines. They're a US company that makes CVD machines for research institutions, for colleges, and they also do production of CVD machines. One of the things that happened when we approached them was that their machines were not built for the application and the type of CVD, the unique character of the CVD that we create. And so they've had to go back, modify their machines to increase the temperatures and make some other adjustments. And in doing so, our CVD is directly deposited. There is no metal that's sacrificed in the process. That speeds up the production process significantly because as no metal is sacrificed in the deposition process, the machine doesn't have to be cleaned between applications. In fact, it just needs to be purged of some of the carrier gases. The carrier gases we use are primarily argon, and then there's some hydrogen and nitrogen in there. But instead of having to clean all of the waste metal that's been sacrificed, we just purge. So that speeds up the process by about an hour. Even in the production process, each substrate takes about 6 hours because of our unique process. There are some issues with laying down graphene directly on our substrate. And so we have solved that and some other issues that relate to graphene on particular substrates through additional layers, and that takes some time.
And so we're working currently on so we do make the material, we make the wafer, but we're also collaborating and we're looking at a pluggable that actually is beyond transmitting data on light. It actually gets into the logic computation. And so we're working on a pluggable device with partners. And so all enabled by our substrate. As I mentioned, I'm sitting here in Yorba Linda, California. We have a location that we're acquiring, and we're building a laboratory and fabrication center, and it's actually up in California. It's in the Central Valley of California, where there's some explosive growth going on up in that area, and we were excited about that, and looking forward to being able to produce quite a bit of wafer product for our partners. So we can talk about some other things. I thought I'd maybe go to questions, because if you have questions, we can always come back to some more discussion that about what we're doing. But I think maybe what we'll do is open it up to questions right now from anybody.
Paul Gill raised his hand. I see.
Paul, do you have a question?
We have a few questions here. Let's go with. Hold on.
Hi. Okay, great. I'm unmuted here, so
Good.
apologize. Chemical vapor deposition has been around for a number of years, and so my understanding of it is, is this the version that's in a vacuum tube and you're firing a laser at some graphite material to create the vapor to deposit onto the silicon or whatever the substrate is? Is that correct, or is there a faster method that you're using?
It's a faster method. We're using induction heating, electric induction heating to heat the gases. We're using a solid precursor that in one of our layers, we're using a gas precursor in another one of our layers. So the company that makes the machines have had to change their machines specifically for our process. They're very excited after reviewing the science on our process. So
Okay.
I really
I'm just trying to
really want to.
understand, just trying to understand how it happens, because you talked about metal contamination as well. I mean, what is the actual material that you are using to create the graphene? Is it carbon, or is it
No.
graphite?
So first, no, neither one of those. We're using a gas precursor. We use methane
Oh, I see. I see.
to separate the carbon and the hydrogen, and then the carbon lays down as monolayer graphene. I don't want to get. We're still negotiating with our company on the intellectual property as it relates to the extensive modifications to the machine. So I don't want to get into too technical
Gotcha.
on how we do it.
So
But the precursor is
yeah.
methane.
Yeah,
Yeah,
gotcha.
in this, Paul, in this instance, it's methane. Astera Technologies, if you take a look at our website and dig deeper, we are involved in creating the substrate. We have other manufacturing that we do with respect to multi-layer graphene, which is a totally different feedstock, totally different IP of ours, different process, different application. So today's presentation is really about the monolayer, and what we're doing in a substrate capacity.
Yeah, it sounds really exciting. So I appreciate your time on that. Thanks very
Sure.
much.
Yeah.
You're welcome.
And I believe that on what Larry's mentioned on the CVD process, the adaptation of our intellectual property onto the partner's intellectual property, the device, the machine, the manufacturing capability is going to be very exclusive, and we're unaware that it exists in the world with our modifications.
In fact, this company has been doing CVD for quite some time, and we're surprised when we approached them with our process, and then their engineers studied the literature and the scientific papers on our process, and they became very, very excited. And in fact, told us what a week and a half ago, one of their engineers told us this is the best way to lay graphene down, and this is the best process for doing it. So on our substrate. There's some other issues that are involved with the substrate and the graphene, and we've solved those. I just submitted Bob will agree. I just submitted the memorandum on why that process is important and how we're going to do it. And we have talked to the company that makes the machines, and their machines will complete the entire process that we need to overcome many of the issues that involve graphene on substrates.
That is really revolutionary. So I appreciate that, gentlemen. Having
Yeah,
been
really
involved in this space since 2014, that's welcome.
Yeah, as a matter of fact, Paul, well, you obviously have a lot of experience. The fact of the matter is our substrate's going to allow stacking of the switches. And so it's a very exciting time, because the enabling effect of the substrate for the photonic compute is amazing, and our partners are very excited because, frankly, they've taken their technology as far as they could on silicon, and so we're improving everything about their photonic. We have a partner with a photonic logic switch device, and so our substrate's going to change their whole thing, tenfold. So we're excited about that. And part of our IP that we have allows that stacking.
And that's what makes the pluggable so exciting right now, is the issue of, the bridge from where we are. If you read the news today, Micron reached $1 trillion valuation, but the chips are becoming very hard to come by, and even photonic chips on silicon, which is what everybody else is doing, they're just RAM chips. You don't have. There's some hybrid chips out there that are in the research phase, but they are not true computing units. And this pluggable that has been developed by Astera staff clearly is the bridge to the future.
Any other questions?
I guess I just want to say a couple more things to Paul, that we have solved some of the. Bob, did we tell them what the substrate is? They know what the substrate is, correct?
Well, we spoke to graphene. Obviously, that's the main player.
Okay, right. So there's some problems with the substrate, some issues in the CVD process. There's some refractive quality issues that we've solved with we've solved those problems. We've solved the dissipation of any heat that's created in a plasmonic effect. We've solved many of the issues that occur when you're trying to do photonic chips. We've protected the graphene during as the fabrication of the chip process. We've solved that issue to keep the graphene from getting damaged during the fabrication as you lay chips down on it. So there's a lot of problems that we as a team have worked through and come up with some pretty solid science on to take this into the future by production. The machines are getting redesigned to allow for fabrication of multiple chips at a time. So it's really an exciting process, and our partners are very exciting to work with.
Sure. I will, I'll talk to you guys offline, definitely, and introduce you to a couple people that I think might be helpful to the process as well.
Great.
And
that's great. Thanks, Bob.
But really exciting to hear this.
And we'll be, and I think we start talking about what our substrate is offline, and some of the issues that arise and how we solve those. I think probably be beneficial.
Great. Look forward to chatting soon.
Okay, Brian, Dave, looking for names. Roderick, any questions? Well, I could talk all day long. I could go and fill this hour up. I don't know if everybody wants me to do that. And this won't be
Brian
our
has
only.
his hand raised.
Oh, did he? Okay.
Brian, you're on mute. I'm not sure if the moderator has to unmute him, but he is on mute.
Lavina, could you unmute Brian?
Okay.
I can't unmute Brian. If you have difficulty to unmute, you can also place your question on the chat or on the Q&A.
Would it be possible for you to talk about your structured sort of approach to listing the company at this point, Bob? Or is that something for another conversation?
Our capital raising plans, is that what you mean?
Yeah, exactly.
Okay. There's a two-pronged strategy. We have a round right now that's called a safe round, and it's $2 million, and it's really an angel moment. And then we have a next round of we're calling that round A, which is 12 million. And we can talk to what SAFE. SAFE is it's an acronym for Simple Agreement for Future Equity. And if anybody on the call doesn't know that, and it's really a placeholder, an investment at this time into that round will.
Can anyone hear me?
Who's
Oh,
that?
yeah, we can hear you. I think that's Brian now.
We can hear you, Brian.
I'm also waiting for my one of my board members, Jose, to join the meeting as well.
Oh, it's Josh.
He goes over all the electrical systems and engineering when it comes to this project. So he should be in shortly.
Okay. Okay, so there's the safe round, and then there's a next round, and
I can not hear anyone. Give me 1 second, guys.
Sure.
We also have questions from TGC. It says, I have the bottleneck solutions due to Arlington, VA, and DC. I only can speak on it with a NDA or after I file something due to national security. Okay, so I think you can connect offline with Bob or Larry after the webinar.
Yeah, I would invite anybody that is on the call, on the webinar, who wants to get deeply into the technology, to contact me. We can execute NDA, documents, and we can get much deeper into the substrate. There are some details about the substrate that is not being mentioned in the webinar today that is important to its functions. And once NDAs are in place, we're very happy to talk about it. And so getting back to the capital, we have a second round. We are calling it round A, even though it's really a second round for 12 million. And that is our capital progression right now. And that's prong one. Prong two is we are considering a transaction that is in a public company. And it's not an organic S1 registration. It would be moving together with an existing company trading on an exchange. The details of which are another issue of right now. We're in an all quiet mode, unfortunately. So, but that's the second prong. So we're waiting for Jose to come in with Brian.
No, I think it was Joshua. He was going to come
Joshua.
in with, but yeah, but
Okay.
Are you part of the Graphene Council, Bob?
We didn't join.
Oh, you didn't join. Okay.
I know
Yeah,
we're aware of all the standards and all that's going on there, but we didn't join.
Okay. Yeah, I mean, I'm not a member anymore as well, but
I think our patent attorneys want us to play this as close to
Of
we have
course.
many provisional patents in, and they're drafting the patent applications, and they keep telling us to be quiet. So
Yeah. Oh, you're just teasing us. That's all right. I appreciate it. That's the public markets.
Yeah. Well, it's kind of an odd thing about, we want everybody to know about it, but we get cautioned by attorneys and things like that. But so our attorneys are Morgan and Lewis, and the main office that we're involved with is in Irvine here in Orange County, California. and we have several provisional patents moving through the system, multiple. And so we have a pretty extensive IP moat, or you want to call it that, several that work together, create a very strong protection mechanism.
Yeah.
Which I'm sure everybody on the phone expects us to be doing, which we're doing.
Yeah, I don't see anyone else talking, so I can keep talking if that's okay.
Sure,
Sure.
right.
Yeah,
Go
sure.
right
Hope
ahead.
you guys don't mind, because
No.
this is my area of interest, for sure. I was involved in the graphene industry back in 2014 when they just after they had the Nobel Prize won by those two scientists in 2009. So the area of application in photonics, and all of that. So you're looking at how would you create that semiconductor? Could you go into that a little bit more?
Sure.
Yeah, we can talk a little bit more about it.
Our partner has developed a switch that works at
I'll put
about
that down.
154 femtoseconds.
Okay.
And so it's very, as you know, it's very, very fast. They say it works at 200 femtoseconds, but in fact it's down to about 154. So that allows for that, whether they're flip-flops or gates, switches, that allows for computing at light speed, producing a real live photonic computer, not just data storage.
Put that up.
Interesting.
Yeah.
I know that Infineon is working on similar opportunities, but they're focused on gallium nitride. Larry, are
Right.
you familiar with that solution?
I am,
Yeah.
and there's some issues with that, and we have done the research on these buffers, and we are certain we have come up with the appropriate buffer for photonic computing and photonic data storage.
Great.
And it's not gallium nitride, it's not titanium nitride. It's really good.
I love it. Okay.
Easy to lay down, not toxic to handle the precursor, just factors that you would consider that was one of the factors we considered in making this commercially a commercial production line. Is the precursor itself, is it safe to store, is it safe to handle,
Right? Of course.
what are the waste products? In fact, it was really nice, we had a call with the manufacturer of the machine, and Bob and I discussed with one of the engineers that we're in California and we need to watch emissions, and our very first call with the team, the complete team, one of their engineers said, "Oh, I now have to. We're in California. I've got to redesign my scrubbers. I can't have a burn box. I'm going to get." So within a week, he had completely redesigned his scrubbers for our lab.
Wow.
And so we have taken into account that this isn't just a laboratory project. This will be production, and they're designing a machine that's not only handles more than one wafer at a time, but also we lay down more than one layer. So therefore, you've got, and the precursors are different, the gases are different. So it's a chambered process with a continuous feed is what they're designing for our production models.
Right.
So really exciting dealing with these guys because they've been in this space for a long time. And it was Bob will tell you, when we had our first call, they were a little hesitant until they read the science. And then they were all in.
And how many different patents pending do you have? And then how many are you going to file? Would that be?
So we actually have 16 and we're going to add 2 more very quickly here.
Yeah, the memorandum I filed today that our attorneys got, that's 2 more patents.
So you've got great coverage, it sounds like, in this. I mean, I know that there's lots of graphene patents that have been issued, but and it's a bit of a spider's web of in that area. So if you could stake out some ground in this area, that would be really interesting.
Yeah. So the interfacing and the encapsulating is a particular niche for us in addition to the graphene plus other materials. So it's a constellation of all those things. And that allows the photonic switch to reach its potential. Light speed compute.
Really interesting. Okay, well,
Yeah.
I think I've got to jump to another thing, but I'm sorry I took up so much time, guys, and hopefully,
No, it's great.
yeah, we'll have to chat again. Thanks very much for the invite, Mitch and Mike.
Is it possible for everybody that's on the call, or maybe they already have it, to get the deck that so my contact information's on the last page. Everybody can get that, or they have it.
There's a question in the chat.
Yeah, there is.
But
Okay.
yeah, your contact information is in the chat. So there's a couple of questions.
So Brian, if you have to leave, thank you for your questions.
Yeah, we
Cheers.
appreciate it.
Bye for now.
Bye-bye.
Okay, so one of the things, the question is, how does the function of your chip affect the computer users? Well, first of all, let's take the elephant that's in everybody's room right now, and that's data centers. So data centers have a number of problems: footprint, energy consumption, cooling, water consumption, noise from the cooling systems. And one of the ones that's not discussed often is the computer waste, and that's the electronic waste. A standard chip burns out on an average of 18 months, so it's 1 to 3 years, and you have this vast amount of electronic waste that includes PFAS chemicals, it includes heavy metals such as arsenic and mercury, and some bromated chemicals that affect hormone cycles. So because we're doing photonic data storage and photonic computing with our partners, the chip, and because of the way we have handled the heat that's generated from photonic, the plasmonic effect of photonic calculations or storage, we don't have fans. So the 60% of a data center that's taken up by cooling systems and space between computers and motherboards, all that goes away. And as Bob said, these become stackable. And so the footprint is now, 5% of what a normal data center would be. To the chips, because we're not pushing electrons, we're using light, and we handle the heat through our substrate. There you go. That we handle the heat through our substrate and through some of the other layers we put in there. The heat is dissipated. Yeah. So the way the heat is handled, there's no cooling system. The substrate handles and some of the other layers, because there is minimal heat that is generated from the plasmonic effect of graphene as you push light through it. So all that goes away. The lifespan of the chip, because you're not pushing electrons and you're not putting heat through there, is substantially longer. So to answer your question, Kathleen, that's that's a differentiation, is all that goes away. Footprint, cooling, the noise, the electronic waste, all that goes away. And the power consumption is now reduced to a fraction of what a normal data center. Now, the pluggable that we've designed, we've talked about different forms of pluggable. One of the keys is right now the bridge is all data centers are on Cat 5 or Cat 8 cables. Your home is on a Cat 6 or Cat 5, and so we have connectors that will connect a storage device that will change the fiber to electrons, for lack of the light to electrons, a connector. So even we could make small pluggables that if you've ever had a portable hard drive and how they get warm because they're transferring those electrons around as you're hitting the RAM. So ours won't get hot. It could be about the same size and have at least 1,000 times the capacity. So a 2 gigabyte or 2 terabyte hard drive is now 2,000 terabytes in the same size. Does that answer your question, Kathleen?
She may need to type into the chat. Kathleen, you want to continue to type? It's about obsolescence, Larry. The function of the chips that we're involved in, are they going to last longer? I think that's
Yes.
Kathleen's ultimate question. And
Yes.
does it assist with the the peripheral elements as well?
One of the things that's available to this substrate is the chips are now putting different modules on the same chip, and that becomes much more possible with a 2-inch wafer. That, again, the calculations of our partner, our computing partners, that they're talking like 100 chips on one 2-inch wafer. So those can have individual functions and individual capacities, and they will last longer because you are transferring light. We handle the heat,
Right.
and therefore there's no degradation in the chip. Also, because of the way we create the multiple layers, the graphene is not exposed to corrosion either.
And so in general, Kathleen, the answer is yes, the computer lasts longer. A lot of it has to do with the heat, and there's very little heat, so there won't be degradation. Where our pluggable is generation 1 of our devices with our partners. We're ultimately going to get to a server that's fully photonic logic based, and that will be the semiconductor inside of it. That's a couple years off, but our first generation device, the pluggable, is a solution for a lot of the issues that exist right now. So We can share, like I said, anybody on the call that wants to talk more about the technology, we're happy to sign an NDA and get deeply into it. So Kathleen, I hope that answered your question best we could. Is the price more? So yes, the price is more right now. It's hard to say with everything that's going on in the world exactly what prices look like in another 3 months or something, but it is a little bit more costly. But your solution is so much faster that there's economies of scale that way.
And your storage capacity in a much smaller space with much less electricity. So, well, we're not selling the monolayer graphene. We're applying it. We're using because it's integral to the machine that's being built for us.
Right. So Kathleen, we're making the wafer itself. And there's more than the graphene that goes into it, and so we're not selling independently monolayer graphene.
Right. Yeah, it's laid down as we produce it. Takes us about five minutes to lay down a wafer, whereas
that wasn't
others,
Kathleen. Sorry, that was somebody else's question. Sorry, but I was trying to answer it.
Okay. So we're using it as we produce it because that's the way the machine is designed. And so other CVD models, it could take 30 minutes, and ours is 5. And yeah, the cost of production is actually pretty low. The total input for a wafer, you're talking about less than $200 for a two-inch wafer. That's with the graphene, that's with the buffer layers, that's with the substrate. So, and that's current cost. It's really nice that the precursors that go into it are, one, not that expensive, and two, for example, I'll give an example. On a 4-inch wafer, you're talking about 20 liters of methane, which is what 0.6 of a cubic foot. So it's not very much. You're talking about, I don't know, less than $1 worth of methane precursor to create the graphene. And we use renewable energy, so we're not buying power. We're off grid, and so we're actually using, just because the quantities are so low, even at production scale, we just buy high quality methane.
Yeah, Larry, the question, Kathleen, is.
Yeah, I saw that.
Yeah.
Yeah, you could. That's we're one of the things that Bob has said from the foundation of this company is, why be a green company if you're not green? So we look at all sources like that. But our power is renewable. We have storage, so we're not on the grid, and we can do all of these things while still being green. And that's why we were impressed with the engineer designing the scrubbers, that he immediately went there, and that's one of our core values.
So Kathleen just wants smart, which I couldn't agree more. I like that. We like to think we're smart. We think we got something. I know. Not necessarily green. Well, so my view of the world is, if we pollute it, that's not a great thing. Let's leave it the way we found it. And that has some green aspect to it, but we're also smart.
Kathleen, a little bit about why I love this company and why I love my partners is that I'm a Go4 veteran, and I'm a 220% disabled. I have neurological conditions. I have lung damage, all from being in a toxic environment for way too long. And so us minimizing our footprint is kind of important to me personally. I don't want to be in another toxic environment in my life. So yes, that is one of the things, is in other applications we do use. Sorry, go ahead, Bob. We use Raman.
Yeah, no, that's true. Larry was in the multi-level graphene. portion, we haven't presented that to you today. We use Raman. We do have technology that's specific to the feedstock with tremendous yields in multi-layer graphene. That's a different component of Astera Technologies. We were focused on this today, but happy to have another webinar and talk about our multi-layer graphene and that technology. But we do use Raman in the multi-layer production.
Yeah, it's important. It's an important step.
No, I don't think we have that up on the site. Happy to provide you with our results if you want to
Yeah,
email me.
and as Bob said, we use different feedstock and different technology depending on what we want to produce, what type of graphene or graphene product we want to do, and what the application is going to be. It's not all, I mean, CVD and the methane precursor with certain carrier gases is specific to putting down graphene and other layers on our substrate. We have other technologies that do other things.
I think we have about 5 minutes more. Anybody else have any questions? Well, if not, I appreciate everybody spending an hour with us. We can do another webinar. Would be great to have you guys back. We could talk about the multi-layer on the next webinar. Anybody who wants to email me for further information, happy to answer questions offline. And for the gentleman, I believe he said he had some national security something happening, that he needed an NDA with us. So it was the other way around. We're happy to execute an NDA on your side and enjoy speaking to you with whatever your issue is. And thanks again for being here.
Yeah, I was an intelligence officer in the Air Force. I understand confidentiality.
Yeah.
Okay,
Now I'm gonna
thank you
turn it.
everyone for
Yep.
your time.
Turn it back over to the host.
Thank you everyone for your time. I will end this meeting. Please feel free to connect with Bob offline. Thank you everyone. Have a good day.